In this video, I want to discuss a few problems from the North American ICPC practice number 7. And the problem set is from Nordic Collegiate Programming Contest 2017. So we had a discussion this afternoon on Zoom, which was led by Chuang. So he discussed how to solve most of the problems in this problem set. So this video can be viewed as a supplement. So I'll give a little bit more hint on some of the 3 of the problems that are used as homework, and go into a little bit more detail in 2 other problems that I think I have something new to add. So I suggest you watch the video for that discussion first, or at least for each of the problems we discuss, you want to watch the corresponding portion of the video first. So first, let's look at the 3 problems that are used in the problem set for CP3. The first one is this import spaghetti. So essentially, the problem asks to find the shortest cycle in a directed graph. So there are a few ways to do it. So I find the cleanest way is to do it using Floyd-Warshall variant. Because for one thing, Floyd-Warshall is arguably the simplest, I guess, non-trivial algorithm. It's just a triple loop and one statement inside the loop. So here, first we need to keep track of information about the midpoint of the shortest path between 2 nodes, because we need to recover the path to be able to print it. We want to print the shortest cycle. Second, we need to, because we're trying to find the cycles, so the way I do it, and I think this is also in the solution slide, is you set the diagonal to max the value. So then you just treat you need to treat a node to itself differently. So when you start, you don't have any path from a node to itself, and because you're trying to find the cycles. So unlike in the default case, you set them to 0, because you can view that you take 0 step and end up at yourself. So I highly suggest do the version with Floyd-Warshall variant, because I think it will make you understand Floyd-Warshall a little bit deeper. So the next problem, emptying the Baltic. So understanding what this problem means is a bit challenging. So Chuang had a very clear description of how why how the mechanics of this draining works, and why the sample example gives the answer they give. So actually, it's quite non-trivial to understand how the sample test case works. So yeah, so I guess I don't have much new idea to add. Essentially, it's you want to process the nodes based on they are reachable to the sink, and also they have the lowest seafloor, or the lowest they have the well, depending on which direction you're looking at, I guess they have most drainage. So because you want to find out the maximum drainage for every cell, and each cell may go through different paths to the drainage point, and you want to use the one that's have maximum drainage. So you want to process node based on that priority. So the structure of the algorithm will be similar to the Prim algorithm for minimum spanning tree and Dijkstra for shortest path. So for the distinctive character problem, so again, this problem we discussed quite a bit in that video. So the problem is we want to find among 2 to the k possible values. We want to find one value with the maximum distance to any existing value. So in k is at most 20. So this is 2 to the 20 to 1 million. That's totally doable. So in my view, this problem conceptually is very similar to this problem that we used as example in CP1 for BFS. So essentially, we are trying to determine the age of a tree and using this tree ring structure. So then things that are directly adjacent to the border have ring level 1. And then anything that touches it will have ring 2. And then we want to find out this. So that's essentially the same as here. So any value that's already provided, those have distance 0. And any of their adjacent value will have a distance at most 1. And then the ones touching a distance 1 will have a distance 2. So it's essentially the same problem. It's just that here we have just a 2D adjacency. Here we have a KD. If you want to think, you can think of a k-dimensional cube. But essentially, for any value, there are a k value adjacent to it. So that's all that's different in terms of coding from the difference from the code for the rings problem. So yeah, so next problem that I want to go into a little bit more detail is this Galactic Collegiate programming contest. So again, we discussed this problem, and in the video, we actually talk about quite a few solutions. So what I find interesting is one solution uses this policy-based data structure. So arguably, this is the most complicated data structure that are implemented in the library that you can use in C++, in the standard library that you can use in this programming contest. But at the same time, there's also a solution that uses Unling vectors, Unling arrays. So a little bit more, I guess, a high-level concept is so this problem of trying to find the rank of an object in a sorted set. So if you implement this from scratch, you can basically do a balanced binary search tree, and then you just keep track of the number of nodes in each of the subtrees. So the standard implementation in Java tree set in C++, the set, they use a balanced binary search tree at the implementation behind it, but their implementation doesn't keep track of this number of nodes in the subtree. So therefore, they cannot. The library doesn't directly give you this fast access of this rank. So order log access to the rank. But this policy-based tree can do that because you can specify this in the balanced binary search tree what you want. So another way to, if you want to implement this from scratch and really support this finding this rank, another way to do it is to use a try. So it's essentially you view each number as a binary string. So if int, it will at least 32-bit, and unsigned int at least 32, at most 32-bit. So then you use a try to store the number of objects with each prefix. So so it's essentially be a tree structure, binary tree, except that the part that doesn't have any value, you don't need to have them. So the size of the tree will be at most linear in the total number of elements, and this you can keep track of. You can update. You can keep track of. So that's another possibility using fairly advanced data structure to solve this problem. But this problem, because of the specific nature of this problem, you can actually solve it without any of this advanced data structure. The specific nature of the problem is the score of every team can only improve. So if you have a new event, a team solved the new problem, then its score will increase. Its score actually never decreases. So because of that, you can solve it without using this advanced data structure. So essentially, it suffices to maintain information of the teams that are ahead, not the current team, the team that we are interested in, so the team 1. So we just need to maintain the information of this team. So during context, my implementation is more complex. ended up using one multiset for every number of problems. So for each n, I keep track of information for all teams that had solved n problems. And as I mentioned in the video, actually, I didn't realize multisets actually erase all copy of the value, so that during contest my code failed. But after the discussion with Huang, I realized actually, because we are what we are trying to do is just to maintain information of team ahead of the team one. Actually, it can be done just using a vector. And here is the code I just wrote using just a vector. So this is the data structure part, and then there's the main function. So I keep track of for each team how many problems they've solved and what is the penalty, and then I use this function to compare two teams. So better return true if A is team A is better than B, so you'll be ranked ahead of B. So the rank of B will be all the teams that are better than B plus 1. And I use this vector ahead to maintain all the team IDs that are ahead of team 1. And I use the auxiliary thing because I'm going to construct a new vector periodically. So I use this as an auxiliary vector. So that's the data structure used for this problem. And this is the code processing the event. So I guess yeah. So I use a macro for loop. So when I copy this, I modify that and to get rid of the macro so that it's easier to parse. But yeah. Okay. So we loop read in M event. For each event, this is a team and this is a penalty. And then there are two cases. Either we are updating the team 1. In that case, I will update team 1 score, and then I will go through every team that is currently ahead of team 1, and then I check, is it still better than team 1 now that team 1 score has improved, team 1 has solved a new problem. If it is, I will add it to this n-hat queue, vector. And after I'm done, I just swap this two vector, and then I will clear the n-hat. So because I don't need this, this information is old, so I just clear it. So that's what happens with the team 1 is updated. Otherwise, team T is updated. So I first keep track of information whether this team was better before team 1. Because if it was better, then I don't need to add it to this ahead, because he's already there. I don't want to add it again. So after that, I update the team T's score. And then if the team was not better before the update, but now it is better, then I add it to a head. So that's all the logic is for this update. And then the rank of the team 1 is simply the size of a head plus 1. So I think it's not difficult to see that this logic is correct, but it's a little bit more intriguing why this is efficient enough. Because I'm doing this, going through all the element in this array for team 1 to make this copy. So this could be big. If I have lots of updated team 1 and lots of this, then this could this is not obvious that this would be efficient enough. But in fact it is. So this code passes, and it's not just because it passes not because the test data is not rigorous enough. It actually should pass because the complexity is at most n to the 3/2, so n to the 1.5. And I think, or m to the 1.5. I think m is like 10,000 or something. So that, or even 100,000, that should be enough to pass. So it's a similar complexity as the square root decomposition, and also the intuition is similar. So let's see why this pass. So when would this algorithm perform bad? Well, it will perform bad if I have lots of update on team 1, right? Because the expensive part happens when team 1 is solving a new problem. But if team 1 is updated a lot, is solving a lot of problem, then the number of teams ahead of team 1 will be small. So suppose the team 1 is updated the square root of n times, square root of m times. let's say 400 times. Now, in order for any team to be in ahead, that team must also be updated at least 400 times. So then there can at most be the total number divided by 400 teams that are ahead of me. So any query that's expensive must mean that there has to be lots of other updates for the other team as well. So then the essentially either my team is updated a lot, team 1 updated a lot, but then the head will be fairly small, or the my team is not updated a lot, then it's okay for me to do this expensive operation. So essentially the complexity, I didn't rigorously prove it, but I think it's I think intuitively it's pretty obvious. It's n to the 3/2 bound to the complexity, and the updates are fairly straightforward. So that's what I want to say for this problem, because on the one hand you have a solution that uses the most advanced data structure in the public library. On the other hand, you have a solution that uses just an array, but it does rely on the specific nature of the problem. So first, also each team, so this square root of n thing rely on the observation that in order, if my team is updated a lot, in order for other team to be ahead of me, to make into here, to make the computation hard, there has to be a lot of update for them as well. If in one update the team can gain a lot of points, then this will not be efficient enough. Okay, so finally I want to talk about this kayaking trip problem. Again, suggest you watch the video portion in the portion in Trump's video. So the basic idea is we will do binary search plus a greedy. So again, for me personally, this is the problem that sort of really stuck in my mind when I think about binary search plus greedy. So yeah, so you can take a look and you will see that's why it is. So how the greedy work part is a little bit tricky because there are 6 possible combinations, and 5 of them the order are fixed, but there are middle 2 that are unsure. So this is, I think I use this skill level of beginners, skill level of normal person, and skill level of I guess either experienced or expert. So we have these 6 combinations, and there are 2 of them in the middle. The order is unclear. So the greedy approach, I sort all the kayaks based on their CI values, and then I try to take care of the ones with I guess maybe the order doesn't matter, but I think I try to take care of the one with smaller CIs and try to satisfy them to meet a particular speed target. That means I need to find 2 players, 2 persons whose skill level sum up will be sufficiently high, and I will try to use it the lowest one that's possible. So if I can use this to satisfy this TCI, then great, I'll just use that. I'll basically scan through the 6 possibilities and see which possibility I want for the current kayak. Because anything that if I didn't use so if one smaller lower combination satisfy TI, then any bigger one is okay. So that is why a greedy would work. So then this is my bisection code, and the next slide has the code for the function checking whether a particular target is reachable. So this just read in the number of beginners, number of normal player, number of expert, and their skill levels, and get the M, and then read in all the kayaks constant, and sort that from small to large, and then do bisection. So yeah, so this is my preference of doing bisection is to have the left side, the answer is always less than high. So yeah, you can do it other variant, but just this is just a standard mechanic to make sure your bisection doesn't run into infinite loop. So depending on the middle two combination, which one is smaller, I will use two different functions. So the two functions are largely the same, except there's just two clauses that are switched. So now let's look at the check function. So this is what it is. So just go through all the kayaks, and then first I see whether I can use two beginners. So I need to have enough beginners, and then I want to make sure their beginner skill level would be sufficient. If that's the case, I'll use two beginners. Otherwise, I'll try to use one beginner and one normal player. Otherwise, in this check one, I guess this two normal player, the SM plus SM less than the one beginner, one expert. So I will use this first, and then otherwise use the next one, next one, next one. So if I run to here, that means I couldn't find any way of making the current kayak work, then I return false. If I run through everything, then that means every kayak has been assigned to a person, and with a sufficient level, then I return true. So